Hello everyone, it's a pleasure meeting you all in my mathematics class. Today I have chosen a different topic of discussion, namely the convergent and divergent of divergence of a series. So we say that a series is said to converge if the sum of the terms approaches a finite limit as the number of terms goes to infinity. See what it means is, for example, let me take see you take this, see let me take this series, see this is a series, see 1 to infinity of 1 by n to the power of p. This is a series, this is a series, this is a p series, in fact this is a p series. And you see that the expansion of this is nothing but it is 1 by 1 to the power of p plus 1 by 2 to the power of p plus that it goes up to infinity. Now, we want to know whether this is a series. Try to understand that here every term can be of any number, a rational number. And so we have to find out whether such a series is convergent. We say that this series is convergent if the sum of the terms, sum means addition of the terms, you add the terms, each individual term of the series, then it must add up to, or it must approach to a finite limit. See here, it is a finite limit. See, it must reach a finite limit. If it reaches a finite limit, as the number of terms goes to infinity, that means here it may go up to 1 by n to the power of p up to n terms. But it must, if you extend it to infinity, you see that when the sum of all these terms become a finite number, then we say that it is a convergent series. If it is not, so if it does not converge, we say that it diverges. We say that it is diverges. And also one more thing that you have to know is, for example, you see that there is a series like this, that is, it is minus 1 to the power of n is equal to 1 to infinity. If you take this series, say if you give n is equal to 1, it is minus 1. If you give n is equal to 2, it is plus 1. If it is n is equal to 3, it is minus 1. So you see that this series takes alternate values minus 1 plus 1 plus. So you see that we are not able to determine whether it reaches a finite limit. Therefore, this is also an oscillating, this is called an oscillating series, and it is, we call that if it does not, if a series does not converge, it either diverges or it becomes, sometimes it becomes an oscillating series like this. This is an oscillating series. This is an oscillating series. This is an oscillating series. So, you see that a series diverges if it does not converge or approaches. It may approach plus infinity. We do not know where it goes. You say that it approaches plus infinity or minus infinity. In either case, there is no finite limit, and so we say that it diverges. For example, if people join to discuss about a particular topic or have a discussion on certain things, only when the people have the same mind of approach, they have the same mind of approach, and then you see that they have the same approach to things and trying to find a solution for that. If all their minds are the same, or opinions are the same, almost the same, you see that they will be able to end up with a decision. They will be able to end up with a decision after a long discussion maybe. But if everyone is having a divergent view of about the thing they are discussing, you see that they will not be able to arrive at a conclusion or a decision. That means it diverges. If it is divergent, you see that they cannot come to a conclusion, they cannot take a decision. Okay, so only when the consensus additive, same mind of approach and a positive approach is there, you see that you are able to arrive at a convergent view, a decision can be taken. Otherwise, decision will not be taken. That means it is a divergent. The opinions become divergent, that the decision is not possible. And in cases like this, you see that people may support the views or may not support the views. You see that they are wavering. If they are wavering, is it that we cannot rely on those people, and so a decision again cannot be reached, and therefore this also comes under called divergence. So you see that a series is said to be convergent only if the sum approaches a finite limit as the number of terms goes to infinity. If it is not so, it is a divergent series, and that it may tend to plus infinity or minus infinity, or it may oscillate. As I have given you, it is an oscillating. Here this is an oscillating series. So if you take if limit n tending to a n is not equal to 0, the series diverges. For example, you take this. Now I will give you one more example for convergence and divergence. See, this is AR square. This is geometric series. This is a geometric series. This is a geometric series with R common ratio. R is a common ratio. If R is less than 1, modulus of R is less than 1, this becomes a convergent series. As it tends to infinity, S is equal to A by 1 minus R with R less than 1. Whereas if R is greater than 1, you see that it diverges. If R is greater than 1, it diverges. And you see that the P series, this is called your P series, I explained to you. Here you see that this is a P series. This P series will be convergent only when P is greater than 1. It converges, and for P converges and P less than 1, it diverges. You see that that is why we decide whether the series is convergent or divergent series. One is using this P series test we can use. Otherwise, you have got what is called the comparison test. This comparison test is, you given a series, if you want to decide or whether it is a convergent or divergent series, we compare it with another series. For example, you see that this sigma of 1 by n is a divergent series, whereas sigma of 1 by n square is a convergent series. So we compare the given series with this 1 by n if it is divergent, and if it is 1 by n square if it is a convergent. So this comparison test, we use such series which are convergent or divergent, as the case may be, to decide whether the given series is convergent or divergent. And you have got another one, D'Alembert's ratio test. This is an plus 1th term. If given a series, this is our an plus 1th term divided by an, and if you take n tending to infinity, if it takes a finite value L, and if this L is less than 1, it is a convergent series. If L is greater than 1, it is a divergent series. And here one more raw-based test is there. See, raw-based test. This is called your raw-based test. And this test is limit of n tending to infinity of, it is an by an plus 1 minus 1 if it is equal to L, and if L is greater than 1, converges, L is less than 1, diverges. So this is also another test where we apply, and the convergence and divergence ideas, they are applied, widely applied, about what is a convergent series, what is a divergent series, and how they could be detected, whether the series is convergent or divergent, how it could be decided, and what are the methods of employed, and then what are the applications. I have just briefly given you the applications, but in fact we have to talk in length about the applications. But we are very much worried about doing the problem. That is why I have made a mention of how it is applied. Okay. Now I will explain the working of the convergence divergence problem by taking an example. See, now you see that we will take this, consider this, take this, see, test the convergence of. See, test the convergence of. See here, you have got here, see. See, 1 plus 2 squared by factorial 2 plus 3 squared by factorial 3. So we have to discuss the convergence of the series 4 squared by 12. See, they have to discuss. See, that means let S is equal to, so let you take this S is equal to 1. I can write this as 1 squared by factorial 1, 2 squared by factorial 2, 3 squared by factorial 3 plus 1. So you see that naturally your loss nth term will be n plus dot dot dot. It goes on like this. Now this is your nth term. This is your nth term. Now we have to discuss whether the series is a convergent, whether this series is convergent or a divergent series. Now what you have to do is, let me apply D'Alembert. That's ratio test. See, for which you have to find what is your an. An is very, very simple. It is nothing but your n squared by square root of n. And find an plus 1, which is equal to here n plus 1 whole square divided by n plus 1 factorial. D'Alembert's ratio test is limit of n tending to infinity of an plus 1 divided by an if it is equal to L less than 1, L less than 1 means and so this is what is your D'Alembert's ratio test. Now we have got here now, see, an plus 1 by an is equal to by an plus 1 factorial divided by so this is because you see that this n plus 1 factorial is equal to n factorial into n plus 1. See, and understand that 5 factorial means it is 4 factorial into 5. 5 factorial means what? 4 factorial into 5. So you see that n plus 1 factorial is equal to n factorial n plus 1. So you see that this, see these two will go off, these two will go off, and here you see that this n plus 1 and this goes off, giving you n plus 1 divided by n square. That is equal to 1 by n plus 1 by n square. So limit of n tending to infinity of an plus 1 divided by n is equal to limit n tending to infinity of 1 by n plus 1 by n square, which is equal to L, which is equal to 0, which is less than 1. Therefore, the series, you call this as your series. Therefore, series 1 is convergent. So this is how we do this. I will take more problems in the next here I will do difficult problems here afterwards. So you see that here what you have to do is we have to apply. See, this happens to be very simple and you have got it. Sometimes it will create some problem that it will be slightly difficult and confusing that we will not be able to do. But here in this problem it is very much straightforward. What you have to do is here d elements. Sometimes it may so happen that there's test that you apply may fail, in which case we must switch on to some other test, then decide whether the series is divergent or convergent. Now in this particular case you see that you write this in this form, and I have written very clearly that very easy to write the nth term, that is nth term is an is n squared n factorial, and this is your D'Alembert's ratio test, which says that limit of n tending to infinity of an plus 1 divided by n if it is equal to L, and if this L value is less than 1, then it converges, and if n is greater than 1, it means the series diverges. Keep this in your mind. Now what we do is an, I have written an plus 1 is nothing but wherever n comes. See, here n is there, so replace it by n plus 1. So n plus 1 whole square. Here this is factorial n, replace it by n plus 1. Then divide this an plus 1 divided by an, then you get n plus 1 whole square divided by n plus 1 divided by this. So you see that automatically this goes up. So this is nothing but, as I told you, n plus 1 factorial is factorial n into n plus 1. For example, you see that 5 factorial can be written as 4 factorial into 5. Therefore, you see that I am writing this as the n factorial into n plus 1. Here this factorial n and factorial n goes off. Here already 1 plus n whole square is there. So this n plus 1 and n plus 1 goes off. So you are left with n plus 1 divided by n square, which can be written as, so divide this n by n square, you get 1 by n. Divide this 1 by n square, you get this. Now if you allow this n to tend to infinity, applying this D'Alembert's test, what happens is that you get a finite limit, which is L, which is equal to 0, which is less than 1. Hence, by D'Alembert's test, we can say that this particular series 1 is a convergent series. Okay, we'll see more problems in the coming days. Do not fail to subscribe for my channel. I am giving a